Hi, I'm Donnie Rudansky from Regents Made Simpler, and in this lesson, I'll be going over the lab practical section of the Earth Science New York State Regents exam. This constitutes about 15 to 20% of your overall score, so obviously it's a very important part. And the lab practicals take place before the actual exam with your science teacher in your science room. And the lab practicals, they are split up into 3 different stations, and by each station, you'll have 9 minutes to complete the task. So this lesson will go over exactly what you need to know to prepare for these lab practicals. If you found this lesson to be helpful, be sure to check out regentsmadesimpler.com to access the full course for the upcoming Earth Science New York State Regent exam to get you fully prepared for the Regent. It's only $89, which is less than one typical tutoring session, and there is a money-back guarantee as well. In that course, you will receive a 2-part course to go over all the material you need to know for the upcoming exam, plus video review with visuals of past Regent exams as well, and the ability to contact me anytime with questions regarding to the course. So be sure to check that out at regentsmadesimpler.com. So I'll go through each station now. First, we have station 1, which is identifying rocks and minerals. So you're identifying rocks and minerals, different characteristics of those rocks and minerals. You were given these rocks and minerals to identify. First, you were given minerals to identify. Minerals, again, like talked about in the 2-part review course, minerals are a naturally occurring mass on Earth that has a crystalline structure with the atoms, and you can see that in the 2-part review course. And there's different characteristics that's on the back page of the reference table, but there's different characteristics of the different minerals. A rock is a naturally occurring mass on Earth, and it could include other rocks or other minerals as well. So first, you're given minerals, different minerals, and you have to identify the characteristics of that mineral. So here we have a mineral looking at right here, and there are really 4 things you have to know to identify the mineral for the station. So there's four things that they give you to identify it. One is luster, cleavage or fracture, streak, and then hardness. So looking at this mineral, again, they give you the mineral. The teacher will give you the mineral by the station, and you'll have to mark off the different things, characteristics of this mineral. So first you have the luster. The luster, it's either metallic or non-metallic, which means that it looks like a metal, or it does not look like a metal. So it looks like dull looking. So obviously this does not look like a metal, so therefore this is a non-metallic luster, right? Again, it has to have a metal look. If it doesn't have that metal look, then it's non-metallic. It looks like earthy, it looks dull, so therefore it is called non-metallic. So we'll see another example of metallic looking mineral, but it has to look like it's a metal luster. Cleavage versus fracture. So you have cleavage versus fracture. Cleavage is that the mineral breaks into somewhat smooth sides, but you can see like flat sides all around it. So this one has cleavage because you see it has flat sides all around it. You see flat sides here, flat sides. It's not so smooth, but it's just like flat sides would be cleavage. This would be an example of fracture. You see, this is fracture. You see how it like breaks into all these different parts. There's not like flat sides to it. So therefore, this would be fracture. This would be cleavage. This would also be metallic. We'll see that in a minute. But this would be cleavage. You see it has the flat sides. You then have to identify the streak of it. You're going to take the mineral and then streak it across like a piece of paper you're given, and you have to see the streak that comes along when you press that mineral against the surface. Will it have a color to the streak, or will it have no color, which means it's colorless, or it'll have a white streak? So either it has a color like a yellow or black kind of streak when you streak it across a surface, or it has no color or it's white, and therefore it'd be colorless or white. In this case, I'm not sure exactly the mineral, but if you rub across the surface and it has a white streak or it doesn't have any color, then it would be this option right here. But if it had a streak that was like yellow or black, then it would be a color streak. So that's really how they identify it on this station. Lastly, they give you a glass plate, and you have to take the mineral and then scratch it against the glass plate. If it scratches the glass plate, then it's considered hard. If it does not scratch the glass plate, then it's considered soft. So again, you're given this glass plate, and you have to scratch the mineral against the plate. If it scratches the glass plate, then it's considered a hard mineral. If it does not scratch the plate, it's considered a soft mineral. So in this case, I think this mineral, if you scratch it against the glass, it does not cause it to get a scratch, so therefore it is called soft. So we'll do another one here. This one, again, there are 4 things. You have luster, cleavage, streak, and hardness. They have to identify for the mineral. So first, this is a metallic luster. It has this metal look, so therefore it's called metallic. It also has fracture because, again, it does not have the sides. It doesn't have like the flat sides. It fractures in all directions, so therefore this is called fracture. You then have, if you streak it across a surface, will it give you a color streak? You know, the streak when you scratch it against the surface. Will it give you a color streak, or will it give you no color or white? So in this one, if you scratch it against the surface, it gives you, I think, a black streak. This would be considered color. And then lastly, the hardness, you get the glass plate. You scratch it against the glass plate. If it scratches it, it's hard. If it does not scratch it, then it's soft. In this case, it scratches the glass plate, I believe. So therefore, it's considered a hard mineral. One more one here. This is obviously, this is a metallic luster. You see it looks like a metal, so therefore it's metallic luster. You then have, this will be cleavage because it has the flat sides. So you see this different sides here, that's cleavage. Then it has, I'm pretty sure it has a streak, I'm not so sure. And then you have the hardness. If it scratches the plate, then it's considered hard. If it does not, then it's considered soft. So that's what you have to know for the minerals in station 1. You then have part of station 1, you have the rocks. Now you have to identify different rocks. So again, a rock is a naturally occurring solid mass, and they could include other minerals and other rocks as well inside that rock. There are 3 main types of rocks, which is sedimentary, metamorphic, and igneous. So let me give you a background of those 3. And again, on the reference table on pages 6 and 7, on page 6, you see the rock cycle and how those rocks are made. And then you have 7 and 6 shows you the different characteristics of igneous, metamorphic, and sedimentary. You are given these charts for the reference for the station to identify the rock. So first you have sedimentary. So this is just the background to understand how to do the station. You have sedimentary rock. A sedimentary rock is when sediments are just pieces of other rock. They compact, which means they come together, and then they cement, which means they get cemented together to make this sedimentary rock. So you see sedimentary rock has these sediments like glued into it. So to identify a sedimentary rock, you will see like it has these sediments. Really, it's called clastic, the texture. It's clastic fragmental, which means it has fragments just like glued into it. That's called sedimentary rock. That's really how you identify a sedimentary rock in this station. If you see also another sedimentary rock that you'll identify in the station is going to be, you see it says on the bottom here, these are chemically and or organically formed sedimentary rock. So sedimentary rock could also be formed by, if you see here, compacted plant remains or cemented shell fragments, because you have dead organisms that were pushed together by rock to form these fossils of plants or of other animals. So if you see a fossil inside of the rock, that will be a sedimentary rock. Because sedimentary rock, they cause these fossils to form. Igneous and metamorphic will destroy these fossils. Secondly, igneous rock. Igneous rock is going to be when hot liquid rises to Earth's surface. So you have the magma, it rises to Earth's surface by a volcano. And you see there's 2 types of ways that igneous rock forms. It either forms inside the ground, intrusive, or extrusive, volcanic, outside on the surface. So what happens with extrusive is that the hot liquid, the magma, rises to Earth's surface. It's called lava when it rises to Earth's surface, and then solidifies. This lava solidifies into a rock called igneous rock. That's extrusive rock. And extrusive rock, since it cools down very quickly, therefore the minerals, the atoms don't have a time to align themselves to form crystals, so therefore they will be glassy. See, it has this glassy texture, which means that it has no crystals. So therefore, it's it's igneous rock. Or it could have these vesicular, you see vesicular, which is gas pockets, because it bubbled and then it solidified so quickly that the bubbles didn't have time to fill in, and therefore you have these bubbles in the rock. So if you see bubbles in the rock, or you see this glass-like structure, that would be an igneous rock. That would be igneous. Also, rock that cools over time, that cools inside the ground, the magma, it cools down over a long period of time, and therefore the atoms that are in that magma is able to align themselves and form big crystals. So if you see here, intrusive rock, like discussed in the review course, will have coarse or very coarse crystals, which means very big crystals. So you see like granite, you see these crystals are very large, you can see them. So therefore, because it formed inside the ground over a long period of time. So if you see a rock that looks like this, that would be igneous rock. It has the large crystals. Lastly, you have the metamorphic rock. Metamorphic rock could form in 2 ways, one by regional and by heat or pressure. So by regional pressure is that when the plates collide, when the rocks move together, because like we talked about in plate tectonics, the rocks move together. What's going to happen is it forces these rocks to be pushed together very, very much, and this is called regional pressure, because you have heat and pressure pushes the rock together, forming metamorphic rock. So you could have sedimentary, igneous, or other metamorphic rock that is pushed together to form metamorphic rock. So for instance, if you had shale, you see shale over here, this is a sedimentary rock shale. what happens is if it's pushed together, it will form slate. So we see here, and you see the way to identify a metamorphic rock is because it was pushed together so much that it forms these like banded structures here. See this banded over here? It's banded. It's like, different lines, and that is called foliated. So you see the texture there? It's called foliated. That's either by mineral alignment or by banding. This is banding. You see like it looks like different things. So if you see a rock that looks like this, it's gonna be referred to as metamorphic. So really, they're gonna ask you to identify it as well to give it a characteristic. You can just write foliated instead of writing mineral alignment or banding. You just write foliated, and that will cover all metamorphic rocks. They'll have that foliated structure. There's also contact metamorphism, but you won't find a rock that won't be easy to identify, so they don't give you those types of rocks. So they just give you rocks to identify if it has a foliated look, that has these banding look to it, and that would be considered a metamorphic rock. So in the station, they're going to give you a rock, and you have to identify if it's sedimentary, igneous, and metamorphic, and then describe what characteristic of the rock caused you to say that it's sedimentary, igneous, or metamorphic. So again, to identify as sedimentary, it's clastic, which means like it has fragments to it, right? It has sediments in it. Fossils, it could have, like we saw before, that you had the fossilized plant remains, or by the bituminous coal, because by igneous and metamorphic, it will destroy those fossils. So fossils are only found in sedimentary rock. Igneous, again, it has that, glassy, because it formed very quickly on Earth's surface, so therefore the crystals didn't have time to form. Or it has the gas pockets, like we saw before. Or it has, in granite, it has the very big crystals because it formed over a long period of time. Then you have metamorphic. You can just write if it has that, like, the banded structure, which we'll see soon. That's called foliated, because the rocks were pushed together to form these like bands. You just write foliated. That's the best way to identify that it's metamorphic. So here is a rock that you'll be given, and you have to identify is it sedimentary, igneous, or metamorphic, and then describe the characteristic that told you that it was sedimentary, igneous, or metamorphic. This is going to be igneous because, again, it's glassy. The crystals didn't have time to form. This is glassy texture. So therefore, that would be a characteristic that has glassy. It's a black texture. So therefore, it is an igneous rock. You then have this one here. So this is going to be metamorphic. You can see the bands here, again, because the rock was pushed together very tightly. So you see these lines here, that is banding. So again, that's metamorphic. And the key characteristic will be foliated. Again, it could either be a mineral alignment or banding, but really just write foliated to cover both. If you just write foliated for metamorphic, that would be the right characteristic to show that it has like these different lines because it was pushed together so much. This rock here, you have the sediments glued together, so that is called sedimentary rock. And again, you can write that its key characteristic is that it's clastic, fragmental. You can write it has pieces all glued together, sediments all glued together. Those would be correct key characteristics to that answer. Here's another one. You see it has the gas pockets that is not filled in. By pumice we saw that, and that is vesicular. So that is going to be igneous rock. And you see how it doesn't have the lava was bubbling and then it cooled down very quickly. So therefore the bubbles weren't able to fill in, and therefore you have these gas pockets called vesicular. That would be the key characteristic. Again, you're given the reference table for the different rocks for this station, so you can look at it and refer to it to get vesicular or glassy or coarse crystals or foliated, those terms. Here's another one. You see the big crystals, coarse crystals, and that would be igneous as well. Again, it formed deep underground, and the atoms had time to form into crystalline structures and form these big crystals like by granite. So therefore, the key characteristic would be the coarse crystals. We have another one here. I see a fossil. Again, fossils are by sedimentary rock. They push these dead plants or animal remains together to form these fossils, sedimentary, and you write has a fossil. So that was station one, which is the rocks and the mineral. So that would be station one, which is identifying different rocks and minerals. Now, station two, which is finding the epicenter of an earthquake. So the way that works is you have an earthquake, which is when the earth gives off a lot of energy through the rocks and causing the earth to move. It's really happens with plate tectonics, but that's discussed in the review course. See, this station is to find the epicenter, which is where the earthquake occurred. So to find an epicenter, you need to find the distance from a station model to the epicenter of 3 different locations, and then using the radius of those 3 stations, you could then find the point where they all intersect. The point where they all intersect is going to be the epicenter. Now, for the station, they give you three different stations that recorded the earthquake. Station A will be already drawn for you on the map, as we see here. This is Station A. It already draws for you the radius around where this is the station model. And again, the radius is where, how far away the earthquake occurred. So we don't know exactly from Station A where it occurred, but we knew it occurred around this, this radius here. You then have Station B already tells you how far away Station B is from the epicenter, and they tell you 1,000 kilometers. And then Station C, you have to figure it out based on information they give you. So Station B, they give you the distance from B to the epicenter is 1,000 kilometers. So they give you how far away the Station B is from the epicenter. You don't know exactly how far. You don't know if it's this direction, this direction. So you have to draw a radius. You have to draw a circle around Station B with a radius of 1,000 kilometers. So 1,000 kilometers, the way to do that is they give you the map distance chart on the bottom of this station. And what you'll do is you'll take a compass. So this is the best compass to really use for this. You may have a ruler and this kind of compass, but either way, let's say you have this compass, which is the best compass to really use for this. You take this compass here, and you're going to line it up, and you see how I have 0 here by 0 kilometers. You have to start here. This is 0, so you start from here at 0, and then you're going to take this red thing right here, and it says 1,000 kilometers, and you're going to align the red thing, the first arrow on the red thing, very important. Do not get confused and do the second one. Do the first one right here, this first one right here, and line it up with 1,000. You're then going to make sure it stays at 1,000 and go to B, and you put this part of the compass over B. You hold it down with your finger, and then you take a pencil and you put a pencil into this first dot here. People make the mistake and they put the pencil in the second dot, but the first dot is aligned to 1,000 kilometers. So you must make sure to do that. And you have the pencil in this first dot here for 1,000 kilometers. You then are going to turn. You see I'm turning the compass here in a circle, and that's going to draw your circle. So you see you're turning the compass. You're keeping your finger on this spot right here to keep it in place, and then you're going to turn it around in a circle to complete your circle. And this will be the circle that really completes it for B. And this shows a circle with a radius of 1,000 kilometers from Station B. So that's Station B. You then have the third station, Station C, and they will give you the time difference between a P and an S. They will give you this chart right here. And you'll have to identify the difference between the P and the S wave. And then based on that, you then need to find the distance from C to the epicenter. So here they give you this right here, and it tells you when the P wave arrived and when the S wave arrived. So the P wave, you see that right here. This is what they give to you. And the P wave, you see how it arrived 5 minutes and 20 seconds from when the earthquake occurred. The P wave, again, P waves you have from an earthquake, it gives off P waves and S waves. P waves always arrive first, they're quicker. S waves arrive longer because they're slower. So the P waves, you see they arrive 5 minutes and 20 seconds after the earthquake occurred. The S wave arrival was 9 minutes and 40 seconds after the earthquake occurred. So the time difference between the P and the S wave is going to be, you do 9 minutes and 40 seconds minus 5 minutes and 20 seconds is going to give you 4 minutes and 20 seconds. That's the first part, is to identify what the time difference is between the P and the S wave. And then based on that information, you go to page 11 in the reference table, which is given to you. And this shows you earthquake information, how far away the station is from the epicenter, and then how long the P and the S wave will take to arrive. So we now know that it took the P and the S wave, there was a difference between 4 minutes and 20 seconds from the P to the S wave. So therefore, you take a piece of paper, and now on this reference table, you have, this is 0 kilometers, this is 1,000 kilometers, it goes by thousands, 1,000, 2,000, 3,000, 4,000, and time is 0, 1 minute, 2 minutes, 3 minutes. So therefore, the small lines in between, this would be 20 seconds and then 40 seconds. So this would be 1 minute and 20 seconds, 1 minute and 40 seconds, 2 minutes and 20 seconds, 2 minutes and 40 seconds, and so on. Over here, the kilometers, this is 1,000 kilometers. So this small lines would be every 200. So this is 1,200, this is 1,400, 1,600, 1,800, and so on. Now what you do is, you take a piece of paper, and we have the time difference between the P and the S wave is going to be 4 minutes and 20 seconds. You draw a line by 0 right here, and a line by 4 minutes and 20 seconds. So that's the time difference between the P and the S wave. You then take that piece of paper and you drag it along the difference between the P and the S. Here's P and here is S, until you reach where the line will be at P and this line will be at S. So that's showing that that's 4 minutes and 20 seconds apart. So we know that this location right here, that is the distance from the epicenter for that station. So we see that we're doing that piece of paper to line it up, and we see that's right at this line right here, and that line is going to be at 2,800 kilometers. This is 2,000 kilometers, 2,200, 400, 600, and then 800 is right here. So that's 2,800 kilometers away from the epicenter would be to answer this right here, 2,800 kilometers. You could also, the P wave arrived at 5 minutes and 20 seconds. So, you could look here, 5 minutes, 20 seconds, and the S wave was 9 minutes and 40 seconds, which was right here. So either way, to find the distance from C to the epicenter. Now that you have that information, you can then draw the circle around C, because we know the distance from C to the epicenter is 28 kilometers. You can make a circle with a radius of 2,800 kilometers. So again, you take your compass, and again, you're going to put this line right here at 0, making sure it's at 0, and then you take this the first arrow right here, and you bring it over to 2,800 kilometers. So here is 2,800 kilometers. Again, you could use a second arrow as well, like if you're doing a higher kilometer distance, but you have to make sure when you draw the circle that the pencil goes in this part right here. But since this line lines up with 2,800 kilometers, I'm going to put the pencil when I draw the circle into this dot right here. So that's very important to keep in mind. So I made that at 2,800 kilometers, and then bring that again. You bring the centerpiece to the middle here, holding your finger down of the center right here, keeping it in place. And again, the pencil goes into this first arrow line, because that's where I lined up this with 2,800 kilometers. If you put it here, you'd make a mistake and get it wrong. So I'm putting it here because that's where I lined up the 2,800 kilometer. Now you draw your circle, again, holding the finger in place right here, and then draw the circle around this whole thing. Now the circle may not stay on the full page. As we see here, it goes off the page. That is fine. That is part of it. You can do that. So you see how my circle went off the page, and that would be station C. So again, we have the 3 circles for station A, B, and C. And then the last step for the station is to draw an X by the epicenter. Now the epicenter is where all 3 circles intersect at the point, and that would be at this point right here. You see how they all intersect at this point right here, because they all have that distance, which shows that this would be the epicenter where the earthquake occurred, with using those 3 stations A, B, and C. So that is station B, finding the eccentricity of an earthquake. The last station is station 3, talking about eccentricity. Eccentricity, like we talked about in the review course, the eccentricity of a planet or orbit around the sun, it's not a circle. It makes like an ovular shape, and that's called eccentricity. Now, eccentricity, this is all right, last station, station 3, talking about eccentricity. So this is the background to it. Eccentricity, again, this is going to be the orbit, how ovular or circular the orbit around the sun is for a planet. In this station, you're going to do the eccentricity of an asteroid that they give you. But first, just eccentricity is how ovular or the orbit is around the sun. So a planet's orbit around the sun, if it's 0, the eccentricity goes from 0 to 1. From 0 means that it's a circle, it's a complete circle around the sun. If it's 1, that means it's a straight line. So if you see here, the planets, they're not at 0 or at 1. You see how they have, the closer you are to 1, the more ovular that orbit is going to be, the more elliptical. That means elliptical basically means oval. And if it's closer to 1, so you see Mercury has the biggest oval, biggest ellipse, eccentricity around the sun. And you see here, Earth actually has, Neptune has the most circular. Again, 0 would be a complete circle, but if it's near 0, it's close to a circle. So again, that's eccentricity. And if you see here, when it's at 0, that's a complete circle. But planets don't have that. They have slightly elliptical, which means ovular. See 0.02, and you have and then you have 0.02, and then you have also in eccentricity, you have the foci. The foci are 2 points that are equidistant to the center of that circle, of that oval right here. So that's called a foci. So you have the sun is one of the foci when we talk about planets orbiting around the sun. The sun is at one foci, and the other foci is an imaginary point in space that is equidistant with the sun to the center. This is the center of the circle. So therefore, the 2 foci are 2 points that are equidistant to the center. And that is how you find out the eccentricity, which is the distance between the 2 foci and the length of the major axis, which is from one endpoint to the other endpoint through the sun. That's called the distance between the foci. That's on page 1, and that's the equation they give you to find the eccentricity, which is the distance between the foci divided by the length of the major axis. That's from this long point all the way to the other end of that oval. So this would be even a bigger eccentricity. See how the foci get further apart and it gets bigger. And 0.4 and 0.5 and so on. Now, also important part of the station is that the closer the planet is or the asteroid is to the sun, the greater the gravity is going to be, the greater the pull of the sun's gravity is going to be on that planet or asteroid, and therefore the faster it'll move in the orbit. So the closer it is, the greater the gravity, and therefore the faster the orbit. So on station 3, the eccentricity, the way they give it to you in this station is you want to find the eccentricity of an asteroid. So they give you the sheet of paper here, and you're given a cardboard. You put the sheet of paper on a cardboard, and they give you 2 points as the foci. So here are my 2 foci here. So again, the 2 foci are 2 points at an equidistant to the center of the ellipse. So here are 2 foci that they give to you. And then when they give you that foci, you're going to take these 2 push pins that you're given as well. So here's 2 push pins, and then you put 2 push pins, and you push the paper into the cardboard using the push pins. So we have the push pins now. That's the first step. They give you a piece of string as well, and a pencil. So you have a pencil and a piece of string. You then take that piece of string and you loop it around the 2 push pins. You then take a pencil and you have to draw the pencil back so that you keep the string taut, which means like straight, not loose. And you bring it back. You want to make sure that the circle is able to stay in the sheet, which it should be to the foci that they give you. And you're going to make a circle, again, keeping that string straight back. So you want to push it back and make a circle around those 2 points. So here would be a circle that you'll see. So you make the circle, but again, you have to keep the string should be pulled back. It shouldn't be kept loose. It should be pulled back, and that is going to make a circle, and that is your eccentricity of the asteroid that you're given. So this is the elliptical ellipse of the orbit of the asteroid that you are given. So we have this ellipse now. That is the first step of station 3 for eccentricity. Then you take off the push pins now, and now the next step is going to be, they tell you, the next step is going to be to write the word sun over one of the foci, and then write a V on the asteroid's orbit where it will have the greatest orbital velocity. So again, there's 2 foci, and that is 2 points at an equidistant to the center. Now, when we talk about planets or asteroids orbit around the sun is one of the foci. So really, you could pick either this point or this point as the sun. Either one is fine. And let's say we pick this one as the sun. Now, it doesn't matter which one you pick, but if you pick this one as the sun, you then have to write a V for which one has the greatest velocity. Now, in the station, it may be different, like what they want you to write. But basically, you have to identify one as the sun and then identify the point where it has the strongest velocity, the greatest velocity, therefore going the fastest in its orbit. So again, whenever the planet or the asteroid in this case is closer to the sun, it'll have a greater gravitational pull and therefore go faster. So therefore, you'd write V right here or whatever else they tell you to identify it. If you put sun here, then you write V over here. So that's the first step, and that's the second step, in this station 3. Now you're going to have to find the eccentricity of that asteroid. So again, on the reference table, you were given how to find the eccentricity, which is the distance between the foci over the length of the major axis. So first you have to identify the distance between the foci, and you need to round to the nearest tenth. So the way to do that, you are given a ruler. So here is a ruler here, and you have to use the centimeter side of that ruler to find the distance between the 2 foci. So you take that ruler, and you're going to line it up here. And you see here, you need to make sure that 0 centimeters is at one point. And then you could go to here and you see that it goes until, in this one right here, it goes until 2.2. So again, 1 point has to be at 0 centimeters, which is this ruler. Different rulers are different, other rulers are different. And that's at 0. And then you see it goes until 2.2 centimeters. And then you write that here, 2.2 centimeters. And that's the nearest tenth. Tenth is one decimal place after the decimal. So it's 2.2 would be 2.2 centimeters. The length of the major axis, again, that's from this point right here to this point right here, from one spot right here, going through the 2 foci to the other end of that ellipse. So we take the ruler again, and again, you want to start with 0 centimeters on this line right here, and then you go until, and you see that's at 9.2 centimeters. So that's 9.2 centimeters. That's right here. Then lastly, you need to find the eccentricity, and that is the equation they give to you. They give you this equation is the distance between the 2 foci over the length of the major axis. So in this case, it's 2.2 divided by 9.2. So you also need a calculator as well for this station. And 2.2 divided by 9.2 will give you in the calculator 0.2391304. Now, you have to know how to round. So they may tell you to round to the 100th or the 1,000th. So if they tell you to round to the 1,000th, what you're going to do is, so here are some examples of rounding to 1,000th. So 1,000th place, so again, tenth to the 10th would be 1 decimal after 1 decimal place after the decimal. 100th would be 2 decimal places. 1,000th, that has 3 zeros, so that's 3 decimal places after the decimal. So here, as an example, we have this one right here, which is 0.145631598. And if you see here, you do 3 points after 3 places after the decimal, which is 0.145. So it's right here. And then you look at the number to the right of it. So if it's 5 or above, therefore you round up this number to 6. If this number right here was less than 5, if it was 4 or less, then it would stay at 5. In this case, it's 0.145, and this is a 6. This number is at 5 or above, so therefore this gets rounded up to 6. So this would be 1.46. You then have this example here, 2.4383. 21476. Again, nearest thousandth, it's 3 places after the decimal, which is at the 8. And you see this number is a 3, which is less than 5. So therefore, this stays at 8. That's how you round down. If it's less than 5, you round up. If it's 5 or more. This example here, 1.943533256. And you see here, this is 943, which is nearest thousandth. And this number is a 5, which is 5 or above. So therefore, you round this up to 4. And lastly here, 5.6632. You see here, 3 decimal places after the decimal will be 0.663. And that's 663. And this is a 2. So therefore, you round down. You keep it at 3. Therefore, with the eccentricity of this asteroid, which is 0.2391343, therefore, to the nearest thousandth is going to be 0.239. That is 3 places after the decimal point. And then you look at this one right here, which is a 1, and that is less than 5. Therefore, you round down to 0.239. If this was 5 or above, you'd round up. But in this case, it's less than 5, so therefore you round down. And the answer would be 0.239. That would be the eccentricity of this asteroid that we are given. Now, the last step for this station in this lab is going to be that we have the asteroid's eccentricity, which is 0.239. In this station, you are then given another planet. There are 8 planets, so you're given another planet, and you have to identify that planet's eccentricity to the nearest thousandth. So on the reference table, they give you that. It's already rounded to the nearest thousand, so you don't have to round it yourself, but you just have to list it. And again, they give you a planet, so it could be one of the 8. So in this case, let's say they give you Mercury. So they would ask you for Mercury's eccentricity, or they would actually ask you for Mars or Jupiter or Saturn. But in this case, let's say they ask for Mercury. You then see Mercury is right here at 0.206. So that's the eccentricity of the orbit is listed right here in this column. And that's at 0.206 would be how you have to list it for Mercury's eccentricity or whatever planet they give you for that station. Then what you're going to have to do is they're going to ask you, does the asteroid's orbit around the sun have a smaller, larger, or equivalent ellipse compared to the planet's orbit around the sun? So now your asteroid's orbit around the sun, does it have a smaller, larger, or the same ellipse compared to the planet's orbit? Now, ellipse again is how ovular is how oval that orbit is around the sun, and eccentricity is how elliptical, how ovular that orbit is going to be. Again, if it's close to 0, 0 means a perfect circle, and 1 means a straight line. So if you're close to 0, therefore it's going to be more of a circle, and if you're 1, close to 1, that's going to be a straight line, and therefore the closer you are to 1, therefore the greater the ellipse, the greater the ovular orbit of the planet is going to be. So if we see here, the asteroid's eccentricity is going to be higher than Mercury's eccentricity. Since it is higher, therefore it is going to have a larger ellipse, because the higher the eccentricity, the closer you are to 1, the greater the ellipse, the greater the ovular orbit around the sun that asteroid or planet is going to be. So this asteroid in this case has a larger ellipse because the asteroid's eccentricity is higher and therefore closer to 1, and therefore it have a larger ellipse than the planet that was given in this case, which was Mercury. So that's how you answer station 3 for eccentricity, and that is the 3 stations for the lab practicals for the upcoming New York State Earth Science Regent. Again, it is about 15 to 20% of the exam, so it's very important to know what to expect when you come in for the lab practicals.